Hi, my name is Elizabeth Teal. I'm from Camaton Middle School in Washington State, and you're watching NASA Now.
That does on an asteroid, the astronauts read out the gravitational effect of those planets.
Hi, I'm Matt, and this is NASA Now. At NASA, every part of the manufacturing and assembly process of a spacecraft is critical to ensuring mission success. Today, we'll meet an expert who explains the science behind welding and why a weld that works on Earth doesn't mean it will hold up in space. That's ahead. First, here's what's happening at NASA Now.
Did water ever exist on Mars? Recent images taken from NASA's Mars Reconnaissance Orbiter reveal that it could have. This image of the McLaughlin crater, stretching 57 miles wide by 1.4 miles deep, shows layered, flat rocks containing carbonate and clay minerals that usually form in the presence of water. Scientists also observed small channels close to the bottom of the crater that could have marked the surface of a lake. This observation, combined with the lack of any large inflow channels, suggests this may have once been the site of a groundwater-fed lake.
Building a spacecraft that can withstand the rigors of space takes a lot of testing and design. When the design is ready and it's time to build a prototype, that's where welding engineer Shane Brooke and hundreds of other people have a big role. Shane took some time to give us a first-hand look at the important role welding plays as human beings push further and further into space.
Welding is used on everything. We use it on engines, we use it on cryogenic tanks. It's used with the space frame of the shuttle. It's used in electronics. So there's a wide array of welding processes that a lot of people don't give credit to, but that are indeed welding processes. Generally speaking, there are two types of welding. There's fusion welding and solid state welding. Some of the fusion processes we're more familiar with, that's the stick electrode or the gas metal arc welding, mostly what you find in shops and garages across America. The solid state welding is a bit different in that it doesn't use melting. For example, if we have this complicated aluminum alloy, it's difficult to fusion weld some of these materials that we create. But we can use the friction stir process because it doesn't melt the material to join the two parts together. There is no external heat source. It's friction alone to heat the material to reach this plastic state. Much like if you were just to rub your hands together really hard and really fast, you generate heat. There are two types of friction stir welding. We classify them as conventional and self-reacting. They both use similar heating processes. Conventional has a one-sided pin tool where we plunge into the part, we plasticize it, form it into like a taffy or a putty. We have an anvil behind the part. So as we plunge into the part, the anvil reacts that load so the part doesn't move, and then it's forged together. The self-reacting process does not have an anvil. So we basically have a shoulder on both sides pushing, canceling out the loads, traversing through the joint. So as both shoulders rotate, the pin will traverse through the joint, the material is plasticized and forged together with a pinching load, and we have a perfectly welded part. Currently we're using friction stir welding for large space vehicle cryogenic tank production. These large vehicle tank structures are aluminum. And aluminum, as we know, is a softer metal than steel. So for the larger space applications, it works great for cryogenic tank production. Looking towards the future at different high-strength steels, we're currently working on friction stir technology that will allow us to weld these higher strength steels. Not necessarily. Different materials have different properties at different temperatures. So here on Earth at 70 degrees, a weld may be great. But if you get into space at minus 300 degrees, where it's very, very cold, now that weld may be brittle. And so what we don't want is that weld to fail when the astronauts need it most. We do all sorts of testing, as you can imagine. There is testing called non-destructive evaluation, where we use ultrasonic technology, X-ray technology, dye penetrant inspection, where we inspect these welds to see if there are any surface defects or volumetric defects. We also do mechanical testing, where we will weld up a test panel, we'll cut it into strips, and we will mechanically pull the weld until it fails. And then based on that strength, or that number, we know how strong that weld is, and then we can use those numbers to factor how safe is it to fly this vehicle.
Did you know that a material used to make jet engine fan cases is also being used in sports and healthcare? Together, NASA and private industry have developed a carbon fiber reinforced composite. This braided, lightweight material is being used to create jet engine fan cases that are stronger and lighter, making them safer and more fuel efficient. This same technology is being used to create more durable, lightweight sports equipment and prosthetic devices. Now you know.
You've just learned how welding is critical to holding together a spacecraft during the launch process and in the harsh environment of space. Now it's time to test your own engineering ability.
Here is a great project where you and your students can build a spacecraft structure strong enough to withstand 3 successful launches. Look for Engineering Design Challenge Spacecraft Structures. You'll find it by checking out the extension activity for this program on the NASA Explorer School's virtual campus.
Well, that's it for NASA Now. Be sure to visit our Facebook page and leave a comment. We'll see you next time on NASA Now.
NASA Now comes to you from the virtual campus at NASA Explorer School.